If you were on the wait list, you should have gotten a message that you are now registered in the course. If you had asked me before about the possibility of auditing the course, I'm fine with that, but I usually ask that you register for the course under audit rather than just sit in it. One or two of you talked to me about it, and I said if there are too many people who have to turn some back, I would turn back those who are auditing in favor of those who take it for credit. It turns out we're not in that situation, so if you want to sit in and audit it, please do register for it, and I will approve for you to audit it. We're still talking about information theory, and we're almost finished, but I posed a question for you. I hope you had time to consider it. And the question was, if there is a distribution out there, now we don't know what it is, we just get examples from it, and we're trying to build a model of it. We're trying to build a probability distribution that is similar to it in some sense. And if we have many people working on that problem, each coming with their own different model, their own different method, how do we know which one is better? It's a question of how do you choose among different approximations of the true distribution where you don't know the truth. You can only see examples that are drawn from the true distribution. Now that I mentioned the problem, let me go back and summarize, as I always do, the elements of information theory that I wanted you to become familiar with. We talked about information. We defined it as log of 1 over probability of an event. Information in events. We talked about entropy. Entropy of a distribution is the expected value of the information under that distribution. This is this P here, and it boils down to, in discrete cases, pi log of 1 over pi. In continuous cases, or in infinite cases, there's an obvious generalization. I introduced to you mutual information, although I never defined it. I'm not sure I defined it officially, so let me define it now. I'm sorry, mutual information, of course I defined that. What I'm talking about is cross entropy. I introduced to you cross entropy. Cross entropy is a function of two distributions, the from distribution and the to distribution. Call it PA, PB. And it's something that looks like entropy, but has a hybrid of the P's and Q's, right? Sometimes they call this P and Q. Maybe I should call it P and Q here. I'll call it PA and PB. So the definition here is sum of P A I times log of 1 over P B I, summed over all I. We saw this expression early on when we talked about the properties of entropy. We just saw it with P and Q. This is sort of a hybrid thing. It looks the same as this, except here, this distribution is the same as this distribution. It's the same PIs. Here they're different. And the inequality that I showed you can be written as, for any distribution PA and PB, the cross entropy between PA and PB is what? What can you say about it relative to the entropy? Is always greater than or equal to the true entropy of PA. And the way to interpret this is, if you call this PA here and here, is if you're measuring your surprise over a long period of time, over events that come from this distribution, P sub A, then your average surprise will be lowest if your model of the world is indeed P sub A. And if your model of the world is something different, P sub B, then your average surprise will necessarily be higher. So this equality here is if and only if P of A equals P of B. If and only if P of A equals P of B. I put 3 lines to say it's an equality of functions, not of numbers. P of A is a whole function, it's a whole distribution. So cross entropy is this hybrid, and it's always guaranteed to be greater than the true entropy from which the events of the source from which the events are coming. Notice that this is greater or equal the true entropy of P of A, not necessarily of P of B. To write something that has to do with P of B, oops, I realize this is really bad for you guys. I started all the way out there. Let me write it here. Sorry, cross entropy between P sub A and P sub B. Just by convention, I put the first argument is the one from which the events are drawn. The second one is the one that you use to evaluate your surprise. Is defined as sum P sub A of event I log of 1 over P sub B of event I. And I said that cross entropy of PA PB is always greater or equal the true entropy of PA. And if I want to say something about PB, it would be the cross entropy from PB to PA. So cross entropy is not symmetric. Cross entropy of P to Q is not the same as cross entropy of Q to P. And there's nothing a priori special about PA or PB. One of them is not necessarily better than the other. It's just that we define one of them as the true one, the one from which the events come, and the second one as the one that's in your head, the one according to which you evaluate your surprise. Okay? So we have information, entropy, cross entropy, and the last issue which we spend a lot of time on is mutual information. Mutual information between 2 random variables. I don't want to call them A and B because there's, let's say, X and Y, is symmetric. First, it's defined as the difference between how much information X tells you about Y, which can be written as the difference between the entropy of Y by itself and the entropy of Y under conditions when X is always known. So that would be entropy of Y minus entropy of Y given X. By the way, this vertical line is used in probability notation for conditioned on. In information theory, you'll often see it kind of at a diagonal. I'm not even sure in which direction. But it's there to tell you that it doesn't mean exactly the same thing. It means when X is known, under conditions where X is known. Conditional entropy given X. Distinguish it from saying what is the entropy of Y given that X takes the value 3. This is still conditional entropy, but it's conditioned on a particular value. Here it's saying under the conditions where X is known, but X could still be anything. So you have to sum over all possible events like this. Okay, because this is symmetric, I can write it equally well as the entropy of X minus the conditional entropy of X given Y. And I can also write it symmetrically as summation over the joint space of Px and Y of log of Pxy over Px py. If you just spell these out, what they mean, and do the right algebra, you will come to this equation. You see it? I mean, this is nothing new. You've seen it last time. But this shows you very clearly, A, that it's symmetric with regard to x and y, and B, it shows you very clearly that if x and y are independent, then mutual information is 0. Because if they're independent, P of xy is always the same as P of x times P of y. This is 1, this is 0. It doesn't show you the other direction. It's not obvious from this expression that every time the mutual information is 0, the x and y are necessarily independent. You could imagine that they may not be independent, and therefore not all these values are 0. None of these ratios are 1. Sometimes they're more than 1, sometimes they're less than 1. But you can imagine if they're sometimes more than 1, sometimes less than 1, the log of it is sometimes positive, sometimes negative. And you could imagine that maybe it could average out to 0. But it's not the case. If they're independent, if they're not independent, then the mutual information is necessarily greater than 0. It's a little harder to show, but it can be shown. Okay, so now let me go back to the question I asked you. And that is, there is a distribution out there in the world. We called it curly D. Maybe it's curly to show that it's mysterious and unknowable. This could be the distribution of radiation coming from the sun. It could be the distribution of acoustic waveforms coming out of someone's mouth when they say a particular word. It could be the distribution of images on your retina, since it could be anything. Usually we're talking about some natural phenomena that we're trying to model. It could be specific to specific instances. For example, distribution of images that contain your grandmother, distribution of weather patterns on days you like to do your favorite sport, or it could be not specific. It could be all distributions of all images. Our goal here is to try to characterize this function from examples. So this is unknown, and in a way unknowable. We're often in a situation where it is unknowable. Namely, nobody's going to come at the end of class and give us the answer and say this is the right thing. But we can draw from it. We can draw examples from it. Sometimes we can draw just a few examples, sometimes we can draw a lot of examples, sometimes we can draw as many examples as we want. Sometimes there's a cost to it, sometimes not. So the examples are going to be x1, x2, x3, etc., where x stands for some potentially multi-attribute, multi-dimensional input, representation of the entire input. And I'm going to write it like this. X comes from the distribution P. This is standard notation in probability theory to say that the random variable x is drawn from or behaves according to the distribution. Is distributed like this function. The actual data that I got will be up to xn. I will call regular D for data. So we all have D, we all have the data, but we have different research groups, and we're in a friendly competition. And we build our models. And one group build the model P sub M1, or shall we call it PA and PB? P sub M1 is good. M for model. So this is, in a way, a syntactic construct. It's something you invented from the data. It doesn't necessarily relate exactly to anything real in the world. And another team came up with P sub M2. And possibly other teams. You can have as many as you want. And now we want to know who is right? Who has the real P sub D in their hand? And what's the answer to that? I thought I heard a word. Sorry? Nobody. There's no reason to think anybody has the right answer. But we can ask, who's the closest? What do we mean by that?
Who has the least surprise?
That would be
probability measure.
Okay, that would be one way of defining closest. Who is the least surprised? Are you going to define who is the least surprised over the training data or over future data?
Like, we'd have to say over training data.
Over training data. Okay? Please.
See how well one team predicts the data of the other teams.
I'm sorry?
You can see how well one team predicts the data of the other teams.
You can see how well one team predicts the data of the other team, but I may not have made it clear, but the data is shared. So D is the same D for everybody. Let me stick for a moment with, sorry, can I have your name?
Oh, Galen.
Galen? With Galen's suggestion. First of all, he suggested we measure how close we are to truth by surprise. And when asked him specifically, surprise over what? And he said surprise over this training data. Does that make sense to you? Do you want to suggest changes, improvements? Or do you want to suggest an altogether different measure? Please.
I think that using future data would be better because it's easy to just match the probability distribution of the training data.
How would you do that?
By just kind of the future
How would you
data.
How would you match the probability distribution?
Oh, by just counting how many examples of each thing in the training data.
Okay. What is your name, please?
Danielle.
Danielle. So Danielle's suggestion is, if your measure was how least surprised you can be with the training data, there's an easy way to cheat. Or maybe you don't want to call it cheat, but there's an easy way to win this battle. And that is, take this distribution, which we call P sub D. This is regular D, not curly D. This is what we call the empirical distribution of the training data. This is a term worth remembering because you will see it in the literature, empirical distribution. Of the training data. Usually empirical distribution refers to the training data. But by empirical distribution we mean distributions are usually probability functions. They are theoretical constructs. But here we're going to define it exactly to match our sample of data. So our data consisted of n examples. That means each one of them has a probability of 1 over n, and all other possible inputs have probability of 0. It's a very weird distribution. Nobody thinks that this is really the curly D, right? But it is a distribution. So let's define it here very clearly. P regular D, not curly D of x, is 1 over n if x was seen in the training data, and 0 otherwise. A very well-defined distribution. It's uniform over the n examples and it's 0 everywhere else. A very weird distribution, but well-defined. And now, if we take our, let's say you're team M17, and if you take P of M17, your model in the competition, to be exactly P sub D, you will absolutely win the competition. At least you will tie for first place. That was your point, right? Do you see why? Because we said that you will be least surprised when your expectations match exactly the distribution over which it is evaluated. It's this inequality here. If you're told that you're going to be evaluating your surprise over the empirical distribution P sub D, then you cannot do better than choose a model that is the empirical. model. So are we done? Should we just take all of machine learning and say just model the empirical distribution and go home? Let me go back to the question of whose model is better. How do you decide which model is better? What are the criteria that you use to define what it means to be better? Please.
Well, I mean, it's good if your training example can accurately predict previous data, but it's not going to be at all helpful of application unless it can predict future data. So that would be the goal.
So you're suggesting that we use prediction of future data?
Yeah.
Okay. That's reasonable. I want to go one step back and say that we don't even have to use measures of predictions or of surprise. What the answer I was really hoping to hear is that it depends what you're going to use it for. When you talk about trying to be close to something, there are many different ways of defining closeness. And you can say, well, it's arbitrary, choose one of them. Or you can say, well, tell me what you're going to be using it for, and I'll tell you which one is a better one. To the extent that we're going to be driven by solving particular tasks, we need to start by asking what measure of distance correlates best with performing well on that task. Sometimes it will be something like measuring surprise, sometimes it won't. I just wanted to make that comment, we'll come back to it, but now I'm happy to go back with you to the common suggestion we heard here of measure surprise over future data. So imagine that you're able to push the button and get more examples after x of n. X of n plus 1, n plus 2, n plus 3, n plus 4, and so forth. I told you that sometimes you have access to unlimited amount of data, of examples. If not, if you don't have access to more than n data items, well, we'll leave that to later, what you can do. But let's assume now that you have access to more than this data item. So this is your training data, and now you're going to have test data. Write it here, it's a little close to the center. Given test data, you can call it, what shall we call it? Should we call it y, or should, no, that's confusing. We'll still call it x. Let's call it x, n plus 1 through xm. So after you push the button n times, you're going to push it another m times. You want to ask which model is least surprised So let's write the expression for the surprise, the average surprise of one given model. We'll start with the surprise itself. It is log of 1 over p, according to which model? The model we're testing, let's say m sub k, or mk, model k, of which event? Of x sub I, where I goes from n plus 1 to m. And because we're talking about average, we want to put 1 over n here. I'm sorry, 1 over m. Does this fairly captures what we wrote here? The amount of surprise that model K experiences on average when seeing the test data. Did I get it right?
Shouldn't it be 1 over m minus n plus 1?
M minus n plus 1. Yes, thank you. I think just m minus n will do, no?
Oh, yeah.
Thank you. So this is accumulating the amount of surprise that model K over time as it is exposed to all these test items, and then dividing by the number of such items. I wonder if I should define this as n plus m. Never mind. This should be good enough. So we're going to do that for every model. Now imagine that you have access to unlimited amount of test data. So m grows and grows and grows and grows and grows. What happens when m goes to infinity? First, don't let it confuse you that you start from n plus 1. Maybe it's not the best notation. You start from somewhere, it doesn't matter. You could start from 1. The idea is that you don't include the training data. But if we call x by some other name like y, and it could start from 1. So that part is not important, where you start from, what the index is that you start from. But what's important is that you see an infinite number of such examples, all drawn from curly D. What happens when you see an infinitely growing, or a sample from curly D that grows to infinity? And of course you divide by the size of that sample, so you're always averaging. What happens in the limit? What distribution does the sample have in the limit? So suppose you had a Gaussian somewhere and you drew elements from that Gaussian. Okay, here's a Gaussian. And you draw an element from here, and another one from here, and another one from here. And you pile them up on top of each other. And you draw more and more and more, and you go into infinity. Eventually, what would be the shape of your empirical distribution? Gaussian. It'll match the Gaussian. Any distribution from which you draw an infinite number of samples, the sample eventually becomes the distribution itself. So in the limit, this becomes the expectation, average becomes expectation. The expectation of this thing under which distribution? Curly D, under curly D, under the distribution from which the axes were drawn. What's another name for this part? Can you say it out loud? I'm sorry? Cross entropy. Between what and what? Look at the definition there. The first thing is the true distribution from which the events come. The second thing is the model by which you evaluate the surprise. So it's the cross entropy between the true distribution P curly D and P m sub k. Now, this is only in the limit as m goes to infinity. So we don't really have this number exactly. But what we do have is an estimate of it based on a finite sample. So this is an argument why this measure, the average surprise over the test data, is A, a reasonable way of comparing models, and B, it's an estimate of the cross entropy between P curly D, which we do not know, and your model. Now this is an important point. We know P sub m, P sub m1, P sub m2, P sub mk. We know P sub regular D. We do not know P sub curly D. That's what we're after. Even though we don't know it, we can estimate the cross entropy between it and any one of the models. How do we establish this? How do we do that? If you don't know P sub curly D, how can you know cross entropy between it and the model? If you look at the definition of cross entropy, it involves knowing both functions, PA and PB. We in this case know PB, but we don't know PA. The way we accomplish this is by, instead of explicitly knowing PA and summing over all possible inputs, we implicitly sample from P sub A, or P sub curly D in our case, and implicitly compute the expectation. This is a very fundamental point. You have a question?
Why don't we actually use a weighted sum in that expression? Because if some sample is really not that likely, then its surprise gets disproportionately disproportionately contributes to the average.
So you're saying, why not put a weight here? The answer is, the right way to do it is not to put a weight there. And that is because if some item gets, that is very unlikely, shows up here, yes, it will affect your average, but a priori, before you see your test data, the likelihood of that happening is small. So you could overshoot, you could undershoot. You have the normal fluctuations of a sample. Hopefully, as the sample gets larger, these fluctuations die down. You're right that there could be pathological conditions under which any reasonable sized sample would have too much of a variance. And we will talk about that. But we'll talk about this notion of variance. But intuitively, you could get unlucky. And you'll have an overestimate or an underestimate. That could definitely be. It won't really be solved by weighing things. In fact, if you weigh them, your expected value may no longer be what it should be.
Because if we have a lot of data, then the empirical distribution will tend to the real distribution. And in that case, we'll have the reliable probabilities and reliable weights in that.
If you have a lot of data.
Yeah, to test on.
So what weights would you have suggested?
Weights from the empirical distribution.
Weight from the empirical distribution means that every item, weight from the empirical distribution is 1 over n. Unless you talk about the case where an item happened to have come up twice. It is 1 over n, so they're all equal. It's a very important and subtle point that in the sample, in your training example or test data, you have side by side items that are extremely rare and some that are not so rare. And in the empirical distribution, they're treated the same. Right? So if you take English and you choose a word at random, it might be the word "the" or some other very common word, or it might be an extremely rare word. There are lots of rare words in English all the time. Under P sub curly D, they're very different. We may not know that, but they are different. Under P sub D, the empirical distribution of the data, they're the same. Except that V is so common that you might see it multiple times. But if you saw two things each once, they would be treated the same, even though one of them might be a lot more rare than another. Okay, one last thing I want to show you is a different way of looking at this criterion. This criterion is very important fundamental criterion for deciding which model is better. And you can also use it to decide how to improve your model. If you have a model and you have 25 different ways of improving it, you can use your measure to choose which one to go after. You can even optimize parameters in your model to try to maximize this measure, this cross-entropy measure. In fact, strictly speaking, it's not cross-entropy, it's a finite estimate of the cross-entropy. And let me write here again this expression. Forget about the notation here. I'll start it from... okay, I'll stick with that notation. I can write this expression and write... Okay, what I'm trying to do here is find the model that's least surprised. I'm trying to find the minimal value of this over all the models. So this is argmin over all models J, models K, sorry, of 1 over m minus n sum log 1 over p m sub k of xi. And by argmin, I'll call it k star. So k would be the index of the model that wins the competition, K star is a standard way of denoting who's the winner. And the winner is the one model that minimizes this expression. So what I'm doing here is writing the same thing but introducing some notation. How many of you have never seen argmin notation before? Okay, so let me just explain what it means. When you write minimum between x1, x2, x3, you know what that means. That means look at the values of x1, x2, and x3 and report back to me the lowest value. If they were 17, 13, and 5, then the answer here is 5. Right? Argmin means something similar but different. Argmin of x1, x2, x3 with the exact same numerical values says look at the values, find the lowest one, but don't report back what that lowest value is. Report back which argument had that lowest value. So the answer to argmin is x3. This is 3? No? Is the answer 3 or x3? Is that what you're saying? Oh. Well, it depends if you're argumenting over all the x's or if you're argumenting over some kind of I. It's a notation thing. But the idea is that computationally, you're doing something very, very similar. You're looking at all the values and finding which one is lowest. At the very end, the last line of code, if you're told min, you report back the lowest value you achieved. If you asked for argmin, you report back the index of the last number, of the lowest number you achieved. Okay? So coming back to here, argmin, everybody contributes their model to the computation. M1, M2, M3 through Mn. I take them one at a time, run them under the index k. I calculate the average surprise of model k under this data. And I remember what was the average surprise for this model. I remember what it was for model 1, I remember what it was for model 2, I remember what it was all the way through model n. Then I look to see which one had the lowest surprise. Let's say it was model 17. Then I report back 17. I don't report back what was the amount of surprise of model 17. In a way, I don't really care what the minimum value was. I only care who achieved that minimum. Okay? That's the essence of this notation. So now that we have the notation, I want to change the math slightly. This would be the same as, first of all, I want to note that 1 over m minus n is some number, some fixed number. Small number, smaller than 1, but it's a fixed real number. It doesn't change the result of who achieves the minimum value. Right? It will not change. It will change the min answer, but it does not change the argmin answer. It changes the minimum answer by a factor of 1 over m minus n. But if all I care about is who achieved the minimum, multiplying everybody by the same number doesn't change that answer. So you could copy everything down and say this is the same as argmin over k without this part. Is that clear why? Whenever you have an argmin or an argmax problem, you can take factors that do not contain the argument that you are maximizing or minimizing over and let them out of the equation. The second thing I can do is I can convert this log of 1 over p to minus log of p. So I'll do both in one step. In fact, I'll do both in one step first. So this is argmin over k of minus some log of p xi according to model m sub k, and this is I goes from n plus 1 to m. The next thing I can do is get rid of the minus sign and change the min to max. That's easy. I multiplied everything by minus 1. I changed the sign, so min becomes max. So I argued that this still remains the same thing. If K star is this, then K star is also this. It's the same winner. The next thing I'm going to do, still argmax here, I have a sum of logs. A sum of logs is like a log of the product, right? So I'm going to write it as log of the product of, I'll write the product this way, P of mk of xi, I goes from n plus 1 to m. Now I want to interpret what this means. Well, let's take another step before I interpret what it means. Log is a monotonically increasing function, which means that whatever k maximizes the log of this expression is also the same k that maximizes this expression itself. I can take the log out. It doesn't change the result of the maximization. Okay? I've led you through many steps that you can do when you have an argmin or an argmax. You can't do them when you have just a min or a max. If it was just a min or a max, you couldn't take out a log. You couldn't take out a constant. But if it's argmin or argmax, if you're just searching who has the most extreme value, then you can take out constants that don't involve the argument k. You can take out a log function. You can do all these things. So I'll take out the log. And what am I left with? I'm left with the winning model is the model that maximizes the product of its predictions over the test data. Now remember that we assume that the test data comes from an IID source, independent and identically distributed. All the inputs come from the same distribution, but the important thing for us here is that they're independent of each other. You push a button, you get a new one, and it does not depend on the last one you got. So I can also write it as argmax over all models k of the probability according to our model m sub k of x n plus 1 through xm. This is the joint distribution over the entire data. So I'm trying to maximize, or I'm trying to find the one model that assigns the highest value or the highest likelihood to the test data. So the same criterion that we used before, minimizing surprise over the test data, is mathematically equivalent to maximizing probability or likelihood of the test data. And you may have been familiar with that criterion before. You may have heard the term maximum likelihood. It's actually used not so much for comparing models, but for constructing models. We'll talk about that too. But it's a very similar concept. If you deal in space of probabilities, you want a model that assigns the highest likelihood to the data you observed. If you think in terms of information theory, you want a model that is minimally surprised by the data you observe. But being minimally surprised and assigning the highest likelihood are kind of the same thing. Questions? Okay, I think we're officially done with information theory. Any other questions about information theory?
Expression notation for the cross entropy, is that supposed to be a semicolon or a comma?
You know, I don't remember. I think it's semicolon. I'm pretty sure it's semicolon. Okay, let's talk about decision trees. So we're going back to traditional machine learning, and I want to remind you of the framework of machine learning. First, there is an input space or instance space, right? We called it X. Then, still within the space of concept learning, as opposed to general machine learning, we're trying to learn a function from the input space to what? Come on, just say it behind my back. In concept learning, we're trying to learn a function from the input space X to... I'm sorry? Say it again.
Yes or no?
Yes or no. To two outputs, yes or no, 1 or 0, plus or minus, Y or N, whatever you want to call it, black or white. And then this defines for us the space of all possible such functions, all possible concepts. How big is that space? How big is that space? 2 to the size of the input, thank you. So we have X, instance space, we have curly C, concept space, and the size of curly C is 2 to the size of the input space. Then there's the target concept, small c, that came from big C. Target concept. Then we have training examples. We call them D. Consists of a set of pairs, x1, c of x1, all the way through xn, c of xn. Here is another example of when you have c of x1 and c of xn, you're not told the true function c. The true target function c is like the curly d, that unknowable, unknown function. All you can have about it is examples from it. And the training data consists of examples of the value of the target function on x1, x2, x3, and xn. So you're given examples of its value. I hope you see the parallel with curly d. Curly d is not about classification, it's not about concepts. It's about the probability of different events. Here we're talking about classification. It's a slightly different problem. But the principle is the same. There is some truth out there. We will never know what it is. But we are only given examples from it. This is what you're given. And then what we add to it is we created a hypothesis space, which we called H, which is a subset of curly C. Called it hypothesis space. And we know usually that H is much smaller in size than big C. Much smaller, and we do that on purpose. And this introduces a bias. It introduces a kind of bias I call hard bias, because it says we're only going to look for the target concept C inside H, even though H might be a tiny fraction of all possible functions. The examples we saw was we defined H to be a function that is a conjunction of attributes, and we showed that it only covers a very small part of the space, and that most randomly constructed concepts are not expressible in that language. So the way we defined operationally the hard bias is by defining a language to represent concepts, and that language defined for us what H was. Anything can be expressed, anything that can be expressed in that language was in, anything that could not be expressed was out. It's called language bias. This actually has deep philosophical roots. There was a guy named Worf, I don't know his first name, was a linguist, I think, and he advocated the idea that language shapes our thoughts. That concepts that cannot be expressed in our everyday natural language, we tend to not think about. And that we may not be aware of it, because how can you be aware of thoughts you cannot have? But that language in sometimes subtle ways shapes the way we think. And this kind of philosophy, this way of thinking, is often called Worfian. The guy's name is Worf. Anybody here knows more about him? Can share with us? It does mean that different languages may shape your thinking differently. Just the very properties of the language before you consider cultural influences and how you're taught and brought up and so forth. The classic examples is that Inuits, natives of the far north of the Arctic, have, I don't know if it's true, but this is the example that linguists pass from generation to generation, have a large number, let's say over 10 number of words for ice. There's dry ice and wetter ice and this kind of ice and block ice, and because they live in a world where ice is very important and making distinctions between different kinds of ice is very important. So it's an example, well, it's an example of two ways how your culture and your environment shapes your language, but also once you're taught a certain language, if it has 10 words for ice, you are naturally make distinctions in your mind. You don't call something ice, you call it this kind of ice or that kind of ice. If this doesn't speak to you, I'll give you examples that I think will speak to you. When I came to this country, I was amazed by how many words they had for cars. Back where I came from, that's Israel, there was a car. Just a car. Yes, there's a truck and a bus. But basically there's a car. For a family there's a car. I didn't know what sedan was. I didn't know what coupe was. Do you guys know what sedan and coupe are? The Americans here say, yeah, sure. I suspect that those of you coming from other countries where cars are not as much as big a part of life didn't have the distinction of coupe and sedan. Another example that's more idiosyncratic, in Hebrew the word for desk and the word for table is the same word. There's this flat surface that you either do work on or eat on, and you don't make a distinction. If you wanted to make a distinction, you would say a writing desk or an eating desk, and it took me a long time to figure out in America when to say desk, when to say table. And I still make mistakes because my mind is not tuned to that. It's not wired for that. And you would find examples like that going from any language to any other language. As you know, there are many synonyms in some languages that don't have a similar number of synonyms in another language. There are distinctions in some language. By the way, I think that tables don't have drawers, but desks do. Is that right? The Americans in the crowd? Okay. I think you can probably think about your native languages, and if you listen to somebody else speaking your language and they use the wrong word, go back to which word it came from, if you're familiar with their source language, and then bring it back. So if I say desk, and clearly you're sitting at a dinner table, if you knew Hebrew, you would know to go back to the word for desk and to realize that it's the same word for table. So these are examples of how, clearly examples of how different languages have different overlaps and different synonyms, but deeper than that, once you grow up with a certain way of carving the world according to categories, it does become the way you think. It's not just the way you express yourself. It is the way you think. Anybody here read Ayn Rand? Atlas Shrugged? The Fountainhead? I'm sorry, I think it's Ayn Rand. I don't know if I'm pronouncing it right. She has one book, I forget what it's called, it's sort of a science fiction terror kind of book about the future world where everybody is taught just one word for the first person. There's no I and we, there's just one word. And they're brought up that way, so they effectively say we all the time. And then it's a story of one person who tries to rebel against it and discovers the concept of I. Which seems funny to us, but if you're brought up without a concept, discovering it is not easy. If you're brought up without a word for it. Okay, so that's the Worfian ideas. Back to machine learning. We can define the bias linguistically. or representationally. This is why it's called a language bias. It's also called a representational bias. I like the term hard bias because it conveys this notion that you're either in or out. You have hard boundaries. Even though this is typically much smaller than the concept class, it's also typically still pretty big. I don't know how to say pretty big, maybe bigger than 1. Much bigger than 1. So it's typically a very large space. I can say maybe it's bigger than big X. It's typically still bigger than the input space. So the input space might have 100,000 possible inputs. H might have 1 billion possible inputs, and the concept class might have 1 quadrillion. Okay, they are orders of magnitude apart. Okay, so this was just to bring up in your mind the framework. Now, what are decision trees? They're actually very simple things. They are a formalism or a language or a representation for expressing concepts. So I'll give you an example, and you can see everything you need to learn from that example. Suppose our concept is play tennis. Very similar concept to play sport. It's basically under what conditions do you like playing tennis. So it's a concept. It has a yes or a no. The input space is some space of descriptions over weather conditions, maybe over also whether your knee hurts or something like that. And here I'll give you a decision tree that implements a particular concept, and it'll be pretty much self-explanatory. If you remember the attributes, one of them was outlook. I'm going to put it inside the square. And again, I'm going to draw lines, one for each possible value of the attribute outlook. So this would be sunny, this would be overcast, and this would be rain. And here, I'm going to put another square. I'm going to write humidity in it. It may be easier to understand if I put question marks at the end here. It's like you're asking that question here. So it's humidity. And again, I'm going to create children here with all possible values. In this case, it's only 2, high and normal. And at some point, I'm going to stop growing the tree and put answers here. So here the answer would be no. Here it would be yes. Here it would be yes. Here I'm going to ask another question. I'll ask about the wind. Wind could be strong or weak. And the answer here is no, and here it's yes. So what I have here is a decision tree where nodes contain in them, internal nodes, contain in them attributes from the input space. If you remember the input space we've dealt with before, it had things like humidity and temperature and all that. Here we use only outlook, humidity, and wind. We don't have to use all the attributes. You can use as many of them as you want, or as few of them as you want. The internal nodes are always attributes. Once you decide on the attribute, that node has children, as many children as there are possible values of the attributes. So most of our attributes were binary. This one actually happens to be trinary, so it has 3. The leaves of the tree are the answers, the classification. And I think it's very self-explanatory how you can take a new instance, a new input from your instance space, and you start at a root, and you ask the question that's sitting at the root, and based on that question you are shunted down to here or here or here, and then wherever you go, you answer any other question, and you make your way down one path of the tree. And then when you get to a leaf, that's your answer. So this represents one particular concept. Question or comment?
Can like the answers to wind go over to humidity, the known humidity?
Can you go from here to here? Right? The answer is no. Then it will not be a decision tree. It would be a decision DAG, which is a perfectly fine thing to have if you want. But we're discussing decision trees. You're right that this would be a reasonable generalization of your formalism. So DAGs, to those of you who are not computer scientists, it should be very few. Why am I writing a DAG? There, yes, directed, acyclic graph. So the difference between a tree and a DAG, so this is directed, right? You can clearly put arrows saying going from the top to the bottom. So this is a tree is a particular class of graphs, of directed graphs. The edges are directed. What other properties do trees have? They are acyclic. You cannot form circles. You can imagine a directed graph that can form circles. Trees do not form circles. But not all directed acyclic graphs are trees. So the example you gave is, you could have an arrow from here to here. This is still a directed acyclic graph, but it's no longer a tree. So the answer to your question is, sure, you could do it, but we're choosing to discuss trees today, and if it's a tree, you can't do it.
Could you make humidity a child of wind? Is that valid, or does each attribute have to...
Absolutely, you can make humidity a child of wind. So I can put humidity here, put a square around it, and split it this way. And you can make wind a child of humidity here, if you so choose. You could even make humidity a child of humidity, but there's not much sense in doing that. Because once you split once on humidity, the value of humidity is already known to be high. There's no point in splitting again. Nobody's going to go in the other direction. So you can assume that any path down will encounter every attribute at most once. It may not encounter some attributes at all. But those that it does encounter, it will encounter them once. Because what's the point of asking about something more than once? You already know the answer. So I defined for you a representation, a language. And the first question that I'd like to come into your head when I define a language for you, when I define a representation of concepts, is what is the bias? So that is effectively asking what concepts can be represented by decision trees and what concepts cannot be represented by decision trees. Remember, we went through this exercise with that language with angled brackets and conjunctions, and you pointed out that disjunctions, for example, cannot be represented. Another way of thinking about the exact same question is, what is the representational power of this language? Namely, what kind of functions can be represented in it? So let's start with that. Let's just ask what kind of functions or what kind of concepts can be represented by decision trees. Let's start with the simplest ones. Can you represent a disjunction of two variables? You have two variables, A and B. Can you write a decision tree that would effectively calculate the concept A or B? A or B? Can somebody help me construct a decision tree that calculates A or B? It's really easy.
Start with A in a box.
Start with A in a box. A can be either true or false, right? So let's say F here for false and true here for true.
And if it's true, you want yes. And if it's false, you want E in the box. And again, true, yes, false.
Thank you. Can everybody see that this decision tree implements A or B? Is this the only decision tree that implements A or B? No. You can switch A and B, you can put B at the root and A down, right? So this already gives us an interesting observation about the properties of this representation. It is not unique. It is redundant. It is possible that two different trees would represent the same concept. I mean, this is a trivial example, and maybe it doesn't generalize, maybe it's only in these cases, but maybe it does generalize to larger examples. Okay, what if you wanted A or B or C? Can you give me a decision tree that implements A or B or C? Somebody who hasn't spoken yet today? Somebody who doesn't know the answer? Come on, you guys. You're supposed to participate. I warned you. Please. Delete the no and put C here. And now split it. False and true. Yes and no. Okay? Check for A. If it's true, you're done. Otherwise, check for B. If it's true, you're done. Otherwise, check for C. If it's true, you're done. Otherwise, no. Well, it's obvious how to generalize this. You can add D and E and F, and you're growing a very imbalanced tree that goes down this route, right? Okay. What about A and B? Can somebody else give me a tree for A and B? Please.
It's the same as that one, just with the falses and trues reversed.
Same as that one. Okay, so you start with A. The falses and trues reversed.
Yeah, so
Should that be enough?
A is false. The answer is no.
And if A is true, then you have to ask about B. And again, false and true. And if B is false, then you know the answer is no. And if B is true, then you know the answer is yes. Unless you want to add a C and a D and an E and so forth, right? So we'll add a C here. No. Yes. I'm going to not bother with writing F and T for binary variables. I'm going to assume always that false is on the left and true is on the right. Okay? So this would be A and B and C. So you're right, the trees are very, very similar. They're almost like a mirror image of each other, except look also at the labels. The labels also have to reverse. Here most of the labels are yes, there's only one label that's no. Here most of them are no, there's only one that's yes. If you're familiar with the Morgan laws from logic, you can see the relationship between these two trees as the Morgan laws. Okay, what about, okay, so let's just observe how many nodes, how many internal nodes are needed to do a conjunction of n variables. So if you have two variables, A and B, you're down to here. How many internal nodes? 2. 3 variables? 3. So we need n nodes for conjunction of A1 through AN. So the size of the tree, as measured by the number of nodes, grows linearly. Same goes for conjunctions, for disjunctions. So you can grow a tree linearly in the number of variables, of arguments. Okay, now let's try XOR. A XOR B. Can you please raise your hand if you know what an XOR is? Okay, so let me repeat what an XOR is. An XOR means exclusive OR. XOR is true if A is true but B is false, or B is true but A is false. And it's false otherwise. So XOR is like a regular OR, but it requires it insists that only one of its inputs is true, not both. So an XOR of A and B, can somebody give me a tree for XOR? Somebody who hasn't spoken yet today? Did you speak today? Please.
So you put A,
A on top.
and then regardless of
False and true.
you still have to check B.
Okay, so you have to check B here. Here, false, true. False, true. Okay, if A is false and B is false, then the answer is no. XOR is not happy in that case. If A is false and B is true, then XOR is happy, yes. Because exactly one of the two, A and B, are true. What happens here? You still have to check for B. There's nothing wrong with putting B again here. Still a perfectly fine tree. And here you have false and true. And if A is true and B is false, XOR is happy, we say yes. And if A is true and B is true, we say no. This is where XOR differs from regular OR. When both A and B are true, XOR is not happy. And if you read the labels off the bottom, they read no, yes, yes, no. Okay, what about an XOR of 3 variables? We have to define it. So how do we define an XOR of 3 variables? The simplest way to define it is associatively. A XOR B XOR C is A XOR B, and then the result XOR C. It turns out it doesn't matter how you do the associativity. You can also do B XOR C, and then the result XOR A. XOR is symmetric, so A XOR B is the same as B XOR A, and it's associative. You can put brackets any way you want, you can do it in any order you want. The reason you can do it is because the result of XOR is also a bit, true or false, yes or no. There's another way of thinking of XOR that's much easier when applied to more than 2 variables. An XOR of n variables is happy when an odd number of these variables is true. And is unhappy when an even number of them is true. So you can think of an XOR function when applied to lots of variables as simply counting how many of the inputs are true or are turned on, and then checking to see if that's an even number or an odd number. Okay, how would you create an XOR tree for 3 variables? Maybe you want to extend this one or create a new one, whatever you'd like to do. Please. One second. Put C instead of every leaf. C here, and C here, and C here, and C here. Right? And then split all of them. Oh my goodness. And this is now false, false, false. There's 0 of the 3 variables that are on. 0 is an even number, and therefore XOR is not happy. False, false, true. Exactly one of the 3 is on. 1 is an odd number, and therefore XOR is happy. No, yes, and this is going to be yes, no, and this is going to be no, yes. I'm sorry. Yeah, yes, no, 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 yes, yes, no. It's going to be yes, no, no, yes. But you can verify that. For example, true, false, false. Exactly one of them is true, so XOR is happy. It's an odd number. True, false, true. It's not happy. Does this tree implement XOR correctly over 3 variables? Yes, nobody disagrees. Okay.
Well,
somebody disagrees.
Except for the one mistake.
What's my mistake?
You have on. Oh wait, never mind.
Okay. Oh, that's fine. I want you to question it and to find problems. Okay, so this tree does implement XOR over A, B, and C. Are there any other trees that implement XOR over A, B, and C? Such as? Switching, permuting A, B, and C. Putting C at the top and then A and then B, or any other combination. You can even permute them in a little more complicated way. You can put A at the top B here and C here. So it could be A, B, and then ask about C here, then A, C, and then ask about B here. So there are many ways of doing that. They all have the same structure though. How many internal nodes do we have there? 1, 2, 3, 4, 5, 6, 7. 7 internal nodes. Can you build a decision tree that have fewer nodes to implement the same function?
In every case, you have to look at every bit, so you have to have that many.
So you think the answer is no?
For XOR, yes.
For XOR, you have to have that many. So what happens if you have 10 variables and you want to build a decision tree for a conjunction? You need only 10 nodes. For a disjunction, you need 10 nodes. For an XOR, 2 to the power of 10 nodes. Okay, so the group minus 1. Okay. So the growth here is exponential. I did not prove to you that you cannot build smaller trees. You're right, you cannot. Proving it is actually very hard, but it has been done.
The way I said is that every path has to have a number of bits. All the paths are different.
But you still need to show that every bit has to be consulted. Maybe it's not as hard as I think. So, what did we learn about the representation power of this mechanism? But we're out of time. We learned that you can represent ORs and ANDs. I want you to figure out by yourself that you can represent NOT, the NOT function, by just inverting the true and false labels actually, or you can sometimes invert the edges. You can represent AND and OR and NOT. You can represent XOR, although it seems to take an exponential number of nodes. So my question to you is now, what can you not represent? What is the bias of decision trees with regard to concepts? What concepts they cannot represent? Think about it. Maybe you should read the book. You should definitely read the book. And I'll see you next time.